So I'd like to thank the organizers for inviting me. It's a wonderful place to be. I would like to begin with an apology. I spoke about this in 2017 at Oberwolfach, and many of you in the audience will have seen me talk. It was a work in progress then, still a work in progress, but the pieces are more or less done, or I think they're done. It just needs to be written up. So let me begin by giving you H. It was quasi-split. Either symplectic or special orthogonal over R. Everything is over R. And let's start with an orthoparameter, an A parameter. Then this A parameter, it gives us a packet of, well, two kinds of packets. Put ABV here. So the one without ABV I will take to be Arthur's packet in his book. That's what, 2013 or something. So these, I will take this to be a set, not the multi-set stuff, but just for the purposes of talk. These are just going to be the irreducible representations occurring in some stable virtual character. Okay, so these things are defined through harmonic analysis. By contrast, ABV, so that's Adams, Barbash, Bogan, in 92, gave a completely different style of packet, something that I will describe shortly. And it's natural then to wonder, are the two equal or not? And so what I would like to do is outline a proof of why the two packets are equal. Just as an aside, I would like to mention quickly, I don't know where to put this, maybe somewhere in the middle, under some special circumstances, when these correspond to representations with cohomology, the ones that were in Dipendra Prasad's talk, then you have another kind of packet defined in yet a different way, Adams-Johnson packets. And so in the special cases, you have these guys. And the experts will tell you that these are a special case of those, although it's not written up. And in this case, these were proven to be equal to these things by Arancibia, Meglin. And Renard, I think in 17, something like that, so quite recently. Arancibia is working on writing up the proof that these are special cases of those at present. Okay, so yeah, I'm just going to erase this because it's a bit cluttered. So how can we prove that these two packets are the same? Well, I guess the obvious thing you could try to do is compute this, compute that, and show that they're the same. At the present time, I don't think anyone knows how to do that. There's some work here that's done. I don't think anyone can really say very much, a little bit about this, but we can't do it. So instead, what I'll do is I will outline the definition for this rapidly, hopefully, and then in terms of twisted endoscopy, and then do something similar over here, look at what twisted endoscopy is saying over here, and show that the two actually coincide. That's the plan. Okay, so I won't actually compute these things. Those things are hard. So here's a quick review of the packets when we're looking at Arthur's situation. So let's take G equal to GLN, and this guy equal to inverse transpose. then you get this disconnected group with two connected components. And let's denote the non-identity component. G without the pointy brackets. I'm going to need this. Okay, so we can choose, we want to somehow look at H as an endoscopic group. So we can choose an element sigma in this non-identity component such that, let's see, the dual group is equal to, or isomorphic to at least, the fixed points under sigma. And we get also some sort of embedding, which I will call epsilon, in keeping with ABV, into the L group of G. In this way, H is an endoscopic group. Twisted endoscopic group. Of this twisted datum. Okay, so we have this embedding of L groups. Why don't we compose the given parameter with that embedding? That then gives us a parameter, an A parameter for GLN. And by definition, since everything is stable in GLN or for GLN, the packet of this guy, well, from this parameter, there's something that I guess people see. If you work in this area regularly, you get an L parameter, and then you take that representation, which is according to that L parameter. I won't write phi sub c there, just phi sub, phi sub, yeah, just c. And that's that. We get a singleton. Okay, and that representation is stable under theta. So let's talk a little bit about theta stable representations. I will denote the set of irreducible representations of GLN like this. Suppose that guy satisfies the theta stability condition. Then we can extend pi to this disconnected group in two ways, right? And they're inequivalent. They differ by a scalar. In two ways, in two inequivalent but we don't want to have this ambiguity, so we fix a Whittaker datum for G, and this Whittaker datum gives us a preferred extension. Which we'll denote by pi plus. So how does that work? Every irreducible representation is a Langlands quotient of a standard representation. The standard representation is generic, so you pick the guy that fixes the Whittaker functional, the extension that fixes the Whittaker functional, and that gives you this guy. So I was told not to put this on the board, but it only takes 10 seconds, so I can't help it. So the twisted character of pi plus is, you denote it like this, trace sub theta pi. I have to apply it to a test function. F Okay, so to every theta stable irreducible representation, we have a twisted character. I feel bad about this, but I'm going to be selfish. I think everyone's read this. I'd like to work with characters, and so I'll introduce the Grothendieck group at this point. Let k pi gr be the Grothendieck group of finite length admissible representations of GR. Okay. A simple way of thinking of this is looking at the free Z module generated by this guy, right? Pi GR is a Z basis for the K group. Okay, I mentioned standard representations. Those are equally as important in this theory, at least the one I'm about to present. Recall, I guess this is due to Vogel, that the set of standard representations they also form a Z basis. Of this Grothendieck group. Moreover, they also have these extensions, preferred extensions, and twisted characters. Standard reps have preferred extensions and twisted characters. So it follows from that, so where is this? It follows from that we can decompose pi psi in terms of standard representations. And furthermore, you can argue the same way and decompose this twisted character in terms of twisted standard characters. Let's write that down. This trace, twisted trace of pi psi, the one that comes from the parameter over here for GLN. This is some integer combination. This is tricky for me. N, J. Okay, trace theta. I will denote standard representations with capital M, just because ABV do that. Trace M. And I'm going to index them by the L parameters that we are allowed to index them by. Okay, so this is some finite Z-leading combination. M, V is standard. And these guys are L parameters. Okay, almost done the Arthur part. Theorem, this is due to, I guess, Arthur. Arancier, Meglin, Renard, which I'll just write as AMR, and self. This is the endoscopic transfer from H. So let me write that down. I like this notation imitated from Meglin. Let's see. H, G, semi-direct product, theta. So twisted endoscopic transfer of what? Well, really it's the twisted endoscopic transfer that gives you this thing. And so same scalars out front, integers. And here we put trace, I'll explain this in a second, of some sort of packet of phi h comma j. No twist. This is on H. Where, let's see, these phi j's, each of these guys is given in this manner for some L parameter on H. And this is the pseudo packet. Sometimes people call it pseudo packet. Pseudo L packet. L packet of this parameter. So what's the pseudo packet? If you're familiar with the prescription for L packets for real groups, well, you know what it is for tempered things, and then you can induce from some tempered object. You take the Langland's quotient to get you the representation, the L packet. So in this case, in the pseudo L packet, we don't take Langland's quotients. We take the full induced representation that we get from the underlying tempered representation. And this thing is stable, and so this sum is stable, and that exactly is the stable virtual character that I mentioned at the beginning of the talk. And so it determines the A packet. And then we can move to ABV. In particular, stable, and Arthur's packet is the set of irreducible representations occurring in here, okay? But I mean after cancellation, right? So there'll be representations that show up here and they cancel out. So what's left, okay? Occurring in, how to say, it's the reduction of that thing. I'll just say this again, as long as you know what I'm saying. Okay? So that's it. Then we'd like to do the same type of thing in the ABV world and show then that we get the same packet. Not only the same packet, we want to show that we get the same stable character. Okay? So let's do that. Now, ABV is a book, and I only have 30 minutes or something, so I have to skip a lot of stuff. My goal is just to give you the objects and to outline how the proof will take the objects in the ABV world and match them up with what we just saw. I won't be able to do a lot of interesting things, but you're welcome to ask me. So, background from the book. Let's take G to be arbitrary, any connected reductive group, algebraic group over R. Okay, so G was GLN before, just for convenience. Now G is this. Well, just to give you a very general picture of what's going on, I will split it into two steps, two giant steps. So ABV, they pair representations with sheaves. Sheaves on topological space X. So I'll have to tell you about that. And then they perform all the interesting work on the sheaves. Okay, so this is what makes ABV, I think, radically different from harmonic analysis. So the interesting stuff is going on here in sort of an algebraic geometric context instead of with the representations. As you'll see, this pairing, it seems like it should be rather artificial, but miraculously it's a pairing that has some sort of content that's sort of connecting the two worlds. So this pairing, when I define it, initially it just seems like an arbitrary pairing, like, seems reasonable, but in fact it's telling you something about the representations in terms of the sheaves, namely reducibility, okay? So the reducibility of representations is mirrored in the pairing through the reducibility of these sheaves. Okay, so I have to tell you about the sheaves first, then I'll tell you about the pairing, and then twisted endoscopy, and then we're done. We can go home. So here we go. Facts about X, this topological space. So first of all, X itself is not the main point. It's a disjoint union of X lambdas, where lambda is the infinitesimal character. You should think about it that way. So these are conjugacy classes of semi-simple elements. And each of these, thank God, smooth complex algebraic variety. You can write it out very concretely in terms of Lag varieties. Smooth complex algebraic variety. This dual group acts on each piece. So I will write X because it's easier, but really most of the work in ABV is on one of these elements. So what is special about this variety is that it replaces our notion of L parameters, the usual one in the Langlands picture. So there's a theorem that says that the G orbits, G hat orbits of X are in bijection with G orbits of L parameters and it's really only the G orbits of L parameters that matter. I should put something in here, maybe like quasi-split. We're not interested in the notion of relevance in ABV, okay? You'll see why in a moment. Okay, so this is a new parametrizing set for L parameters, and it has a richer geometric content. Now let's pick, so we have an L packet. How about representations? I'm aiming to talk about the local Langlands correspondence. So let's say S be an orbit. Then to pin down a representation, we need an irreducible character of a Langlands component group. So let me write that down. In this context, let tau be an irreducible representation. Turns out to be a quasi-character of, what is it? The connected component, the component group of the stabilizer. It's a mouthful. Stabilizer of Y. And now, normally you would look at the stabilizer or the centralizer inside of G hat. We're going to get fancier here. We'll look at the universal algebraic cover. If you take it semi-simple, simply connected, then you can ignore it. Okay, then the local Langlands correspondence looks like this. Yeah. Yeah, the simplest example is like a torus. If T is a torus, then you're looking at all finite covers of a torus. So everything, right? The nth power map is an n covering, and then you would look at the profinite, the limit, right, of all these covers. Yeah, it's not algebraic. That's right. It's pro-algebraic. Yeah, but to reduce the brain strain, you could just think simply connected semi-simple. Okay, it's really not worth thinking too much. I want to add this in to make it show you how powerful their theory is. Tasso Carleton has a similar sort of thing going on, also for p-adic groups. The theory of rigid inner twists. I think I got that right. Okay, so local Langlands then looks like this. We have irreducible representations on one side. On the other side, we have this set capital C, which is the set of all such pairs S tau. Then the local Langlands correspondence in ABV looks like is a bijection. Now, I will write something slightly different over here. Instead of the R points of G, I'm writing G over R. I'll explain that in a moment. It's a bijection between this and this capital Xi. So I have some sort of Xi as tau here, and that maps to a pi Xi in there. So this is more than just the representations of the real points of G. You're including typically other inner forms in the same inner class of the quasi-split form of G. Okay, so you're collecting a bunch of representations from different inner forms, and that's why this this alge appears over here. Okay, so it's giving you a sort of super packet. But yeah, that's all I want to say about that. It won't matter for us, but I thought I would say it all the same. Okay, where are we? Number 3. I have 2 more to go. We haven't talked about sheaves yet. Okay, so we've got a connection between representations and this parameter space. This parameter space gives us sheaves. How does it do that? A pair so this tau is a representation of the component group. The component group is very much like the pi1 homotopy group, and so it's giving us a local system. A local system on S, and then you can extend that by 0. To its closure, and then take the direct image. to obtain an irreducible, constructible, G-equivariant, when is this going to stop? G-equivariant sheaf on, I should give it a name. ABV use mu C on X. I use this word constructible here. I should have said that the G orbits stratify your variety. Okay, so that's one kind of sheaf that's important, and the other kind are the perverse sheaves. That's where I get nervous. So similarly, one may define, again, irreducible, G-equivariant, so on. I'll write it out, irid, equivariant, perverse sheaf, P, C, and ABV, by taking the intermediate extension from S to its closure. Okay, so don't ask me what the intermediate extension is. I certainly won't be able to do that right now. This is easy, but this is rather complicated. So we have our sheaves. We want to pair them with the representations through the Grothendieck group. So I will introduce the relevant Grothendieck groups over here, and then we can talk about the pairing. So let Kx be the Grothendieck group. This is done of the constructible category of the constructible G equivariant category. And it turns out that the Grothendieck group, so hold on. So a basis for this is, a Z basis for this is these guys, okay? It's just that. It's just a Z module, free Z module generated by these things. It turns out if you do the same thing in the perverse category, then the Grothendieck groups are isomorphic. So there's an explicit isomorphism. We will identify those things, okay? So it turns out that the Grothendieck group of the perverse category is isomorphic to X. So we'll identify them, and after the identification, we may regard these guys, the perverse, irreducible perverse sheaves, as a basis, Z basis, for this Grothendieck group as well. Okay, so in the representation theory world, we have two bases for the Grothendieck group, the irreducible ones and the standard ones. In the sheaf theory world, we have two bases as well, the irreducible constructible and the irreducible perverse. So how to pair them? Well, I don't know, initially I thought that you would want to pair the irreducible representations with sheaves. That would be kind of the easiest thing, but remember the irreducible representations require taking of Langland's quotient. So if you want to avoid that, the simpler thing to do, so you might want to start with an irreducible representation and pair it with a sheaf, but the irreducible representations have Langland's quotients involved, and if you want to avoid talking about Langland's quotients, you should start with the standard ones. So there's a theorem, an ABV. It says that there is a perfect pairing between the two Grothendieck groups. Such that. So the definition is through, as I mentioned, the standard representations, and you pair those with the constructible ones. These are the kind of the easier ones from a certain point of view. There are some signs here, which signs? But I will ignore those. So there's some explicit sign, but I will just write it this way. So this is the Kronecker delta function. It's 0 or 1 as well, these are different or not. And so they start with defining the pairing this way. What makes this a theorem, what gives it content, and is that if you pair an irreducible representation with a perverse sheaf, you also get some plus or minus. Again, there's an explicit formula, but I'll just write this. So, why is this difficult, or why is it there's something to prove? Well, you can decompose this into irreducible representations, and you get sort of a change of basis matrix there. Similarly, you can decompose this into perverse sheaves, and you get a change of basis matrix there. So from linear algebra, you know that you can pull those matrices out. And what this is saying is that those matrices are like inverse transposes of each other up to some signs, okay? But the signs are a pain. Right? That's where the problem is. And that's what, well, I'll write the next theorem down. Next theorem is basically the same thing works when you're looking at twisted objects. What time? 40, right? Okay. So theorem, Christie and Arancibia. So there is an analogous pairing. I have to explain what these things are, but you can probably guess. X between theta stable reps and this sigma, you may have forgotten, that defined the H as an endoscopic, twisted endoscopic group. Okay, this sigma is you can think of as an involution, or not, sorry, just an automorphism between theta stable reps and sigma stable sheaves. So by analogous, I mean that you have the same formulas over here, but now we have to worry about which extensions we're using, right? There's more than one extension that lives in each of these Grothendieck groups. And so we have to think about that and make sure that we get the right formulas coming out, the ones we need to get this cancellation. I wrote perfect over here. Here I'm including all extensions, so we shouldn't expect the thing to be perfect. But if I restrict this pairing to the preferred extensions in both of these Grothendieck groups, then it becomes perfect again. Okay. And this, I thought this was actually going to be easy, but it took me a very long time. But it's done now. Okay, so now that the pairing is there, we can move to the twisted endoscopy for ABV. How exciting. Make sure I'm not forgetting anything. Okay. So let's get back. So as you recall, this is Arthur's A packet without any kind of superscript, and this obviously is the ABV L packet. So let's go back to what I had before. So let's return to G equal GLN. All the other stuff, this is important. This embedding of a twisted endoscopic group. Okay, so now we can play with this embedding in the world of sheaves. And the first thing we can do, this might seem to go the wrong direction, is let this map, this goes from Kx. Now, I just wrote Kx before, but now I have to differentiate between the two groups. So I'll put this guy here. So these are this is the growth group of the constructible category. But I have to put a little bit more in here. I have to put this sigma in there. So the ones that are here, right, that are sigma stable. And I would like to restrict to the constructible category for H. And this is just inverse image functor. So for those of you who might not be familiar with this sheaf stuff, this is easy, okay? This is not hard to compute in this picture. At least for constructible sheaves. For perverse things get weird, but as long as things are irreducible, constructible, it's not hard to compute. And then we have the pairing, which is gives us the transpose of this thing, which goes in the right direction for endoscopy. So define epsilon lower star. This should go from the endoscopic group, pi H R, to K pi G R theta by, like I said, it's given by the transpose. So epsilon lower star of something in here, pi C. That's when I pair that with, you know what, okay, whatever, doesn't matter. Okay, that is pi C paired with epsilon upper star of P. Yeah, no, it's okay what I'm writing, but I feel uncomfortable, so I will go back just because it's easier to see what's going on if I do this way. M and mu C. Okay, so let's see. This is the pairing for G, so I should put some kind of indication of that. I'll put a subscript G here. And this pairing takes place on the level of the endoscopic group, H. Okay, and this is what gives us twisted endoscopy in the world of ABV. So if you look at what's happening to sheaves, it's, as I was claiming, rather simple. And as long as the pairing is nice, then this is also not so bad. At least if you look at it on these constructible objects paired with the standard representations. So now, in the last few minutes, I have to make a big leap. So sweeping everything under the rug. ABV construct stable virtual characters eta. See, this is the parameter. Well, this is the a parameter for h, and eta c. This is the parameter that we got from c of h using epsilon, using this thing. So once we have the stable virtual characters, they define the packets from them. Define ABV and pi ABV. Okay, so there's a lot of work that goes into this. Again, happy to discuss it later, I suppose. But let's just take for granted that these things exist. What do I mean construct? They tell you what they are. That's all. They define them, yes. Yes. Well, in some sense, they tell you what they are. Yeah. I can tell you what they are too. Maybe as the question, I can do a quick yeah. You know. Okay. Okay. So great. Now we have them. Now, how do we prove that the packets are the same? I feel confident in writing theorem this time. Here's the theorem. And the proof goes something like this. Let's do epsilon lower star to this stable virtual character that ABV give us. That is equal to this thing, but we've got a theta here. So I need some sort of preferred extension, or it does go to the preferred extension. Okay, so this is only one of these equations is going to be obvious. So let me just put them down and then I'll explain. The next one is that this one, the ABV one, is equal to Arthur's in the GLN case. So this is just plain old that guy, okay, the one we had from a while ago. And if you recall, we decomposed this in terms of standard representations. So let's just write that down. Nj trace M sub C. Okay, that's the same equation. This is the only easy one, right? The one that we had before. And then the last one is that, in fact, that's the same thing as Nj, what we had in the Arthur case. Trace no theta, pseudo packet. Okay, so let's just take this for granted for a second. I have 2 minutes. And then you can show that this epsilon lower star is injective on stable characters, virtual characters. And so we get what we want. The ABV stable virtual character is equal to Arthur's. And then we're done. Okay, so I have 2 minutes, 1 minute. Anyways, let me just say a few words about each one. Okay, this first equality is not easy, but it's something that I claim is already an ABV. They just didn't spell it out. So I wrote a paper with Christie that spells this first one out. It's a fixed point theorem. It comes from the fixed points of sigma on some sort of strange cohomology. Okay. So that's an ABV. The next equation amounts to showing that for GLN, ABV's virtual character reduces to a singleton. Okay, that takes a bit of work. You have to compute things, but it's doable. This is easy. And then the last part, this says that for standard things, transfer in the Langlands-Shellstad picture, or Cartwitz-Shellstad, is the same thing as transfer in the ABV picture. Okay, so that's just raw computation. You can show that. They say it's an exercise in ABV. I'm sort of bitter about that, but it can be done. And yeah, that's all I'd have to say. Thank you. Yes, we need the GLN-ness here. Yeah, otherwise we shouldn't expect this to be a singleton. Yeah, so we use certain facts about GLN, one of which is that the centralizer of the component group for GLN is trivial. We need that. We need that the induced, if you have an irreducible unitary representation of a levy of GLN and you induce, you get something irreducible. There are certain facts that we need, yes. Yes. So is it analog with the... No, it's actually easier in the sheaf case. I can tell you quickly. If you have a perverse sheaf and you decompose it in terms of these irreducible constructible ones, the one that corresponds to... so this is going to be... Okay, so if I take an irreducible perverse sheaf, then this guy occurs with multiplicity 1 inside of this sheaf, okay? And so sigma stabilizes this thing, and that gives me, by kind of like a Schur's lemma argument, that I can choose the one that gives me 1. Can you expand upon your remark about which one? This last one? Last one. Okay. Yeah. So you have to actually check what happens to each one of these things under twisted endoscopic transfer. And those things are doable. You can compute it for these pseudo packets. Okay. You can just write it down. Ultimately, what saves you is you're just using induction, and twisted endoscopic transfer commutes with induction. That's what really makes it not hard. If you try and do it for just, a representation that's not a pseudo packet, then you're going to run into all kinds of trouble. Then you can't do it. At least I can't. Yes. No, yes, you're right. There's some ambiguity here. So the right way of thinking of this is think of this as the free Z module on twisted characters of the sigma stable representations. That's the right way of thinking about it. At the beginning,